Before we start today, today's workshop will be all about participation of customers in our program. We will celebrate a couple of case studies. We will mention some customers that have done work with us really, really hard over the years, over these 5 years. But before we start on that, I would like to give Doug Didburner a couple of minutes to bring up his SciPac message for those of you who are members of SciPac. Doug, please.
Okay, sure. So I just wanted to show of hands how many people know about SciPac or are SciPac innovators. Okay, that's great. So I just want to kind of remind everybody programs they have. So if you're not, you can go to their site. So SciPac, Canadian Industrial Program Partnership for Energy Conservation. They changed one of the words on that one. So there's an industry group and there's a buildings group as well if you're more of a building plant. But they have process integration studies, so it's helpful. It's a really good way to supplement what Enbridge is doing for you. So ISO 50001, if you're looking into that. If you're looking at an EMIS system, they got money to help with that. So I can never read this one right. Fluid dynamic studies. If you have ovens, equipment like that, they can do a study. Process integration is a huge one if you have a really complicated system. I think I said ISO 50001 trading with dollars to cents. A lot of energy information on their website. They've done a bunch of benchmarking for different industries where you can easily look that up and you can compare how well you're doing with your competitors. If you're not doing as well, you probably want to step up your energy conservation. There's still training and dollars to cents, and there's actually a newsletter as well if you want to get an update on what project's going on. I find these are great, like these case studies too, because you take a look at that, you meet people that have already done projects like that, it makes it really easy to do it and to copy them, right? And that's one of the reasons why these things work so good. So if you're not a member, you want to check it out, SciPac, you can just look, I do a web search. If anyone needs me to write that down, just give me just talk to me later on when it's done then. Thank you. Yeah. Some more help for you for free.
Great. So, speaking of help, what I wanted to open today's presentation with is our video. We made this video towards the end of the year. It's not so much about us. What I wanted to focus on this video is a couple of customer cases where they speak of the successes that they had working with our program. So we'll open up with that, and then we'll come back to the presentation of the workshop. You can use energy in a number of ways.
A lot of people don't know. You just pay a bill and say it's the cost of manufacturing, move on.
It's important for our customers to see energy as a controllable cost, because if you don't, you're never going to do anything about it.
What excites me the most about the job that we have at Enbridge is being able to help the customers realize their ambitions and their goals, and to see Enbridge more than the suppliers of energy. We start with the free technical advice, all the way through financial incentives for energy audits, energy metering, as well as implementing energy efficiency projects.
One of the challenges the industrial sector is facing right now is rising costs of keeping their business operating. What we offer that a lot of other people in the industry don't is free advice.
Because the textile industry is a very competitive market, we have to watch out always to keep our costs down. First time when Chris came in, we went through the production, I explained him each process.
The felting machine's steam hood was throwing money off the roof through a fan.
In our boiler room, we have a lot of excess heat. Slobodanka recommended that we put in an economizer that captures that heat and reuses it to heat up our hot water.
We reduced basically the speed of the fan. It's a huge success. We're saving a lot of money with every bill.
Often people would ask, why would you help us save something that you make money off?
Why would someone that sells gas to us encourage us to use less of it? Quickly became apparent that they were in this for the right reasons.
It serves us no purpose if industry leaves the province. So it's in our best interest to help you become more efficient. Keep your doors open and your lights on longer.
Our energy consumption dropped up to 20%, 25%.
Natural gas usage has gone down 43%, which is really unprecedented within our sector.
Enbridge wants our industrial customers to flourish.
Our job is to help manufacturing here be competitive in the market.
If everybody could do something energy efficient, we could be miles ahead.
Your energy?
Our experts.
Smart savings.
All right, so hopefully everybody enjoyed the video. And as I said, it's not about us, it's about the savings that customers had. Pilkington has saved 43% of their natural gas bill, 43%. That made a difference. Pilkington has, when I worked with them way before Slobodanka took over, they were in a downturn. They were close to closing the plant. Now they actually are getting the business from their European plants here. That's what the difference savings made to them. Because once you implement those savings, you implement the mentality that anything can be done, that anything can be improved. Once they improve that, they improve their processes, and now they're thought of as one of the top plants in their Pilkington global setup. The guy who helped us, Ron, that you've seen there, is actually now traveling to all the plants around the world, helping them save energy. That's what we want our program to achieve. We're not worried about incentives. We're not worried about one particular project. We want you to get the savings like that for your plant. So with that, how do we do that? For those of you who have been here on these events before, you know our process, how it works. We really do believe it, and we practice it as much as we can. Knowledge development, giving you information, where to look for energy savings. Opportunity identification, again, where is that opportunity? Quantification. Many people will walk through your facility and will say, well, you can save 30%. 30% of what? Where? How? We will actually help you quantify it. So it's not 30%, it's 23.8%. It is 12%, but we believe in that 12%. Engineering analysis, giving you and analyze and interpret the data that you might already have in the facility. And ultimately, action and implementation, which is up to you to help you save money and to improve your bottom line. Today, we'll focus on knowledge development. So what is knowledge development? What is it? Newsletters that you guys might receive through an email. Some of the web access. We have great new web pages where you can access all sorts of information about energy savings in the industry specifically. So for manufacturing, not for general building setup, not for general commercial buildings, for actual manufacturing. And of course, workshops like this one. And speaking of which, as Isabel has mentioned, this is a 5 years of workshops. We put there all different topics that we have known people to come for this. I don't know how bacon got onto there, but hey, whatever gets people going in the morning, that's good. So again, thank you very much for those 5 years, guys. What else happened? 700 people have showed up for these workshops. 700 people, representing about 150 organizations. That's a great cross-section. When you think about Ontario, you only have about maybe 850 large industrial customers. 150 of them have been here, just like you did today. That's a pretty good show-up. This is what we have done. 350 energy studies. Many more complementary assessments that we have done. So 350 energy studies that we paid for, many more complementary assessments that our ESCs have done. Every time they go to your facility, they actually do an assessment before they go to see how much energy you use, where that energy is going, and then they can talk to you intelligently about your specific use. Not generic use, your specific use. And all of that has resulted in 750 plus project implementations, which means you guys have implemented 750 projects. And what does that actually mean in numbers? It means we avoided using 25 million cubic meters of natural gas annually, or every year for the last 5 years on average. That's a lot of natural gas, equivalent to 46,000 tons of CO2. It means we're saving about $5.5 million annually, every year. That's what helps keep business in the province. And I understand, I know that electricity is far bigger cost to you guys. Natural gas is not such a big cost. However, this helps. This helps your business run better, and the energy efforts that go into natural gas conservation are the same that go into electricity conservation. That means that you can reduce both of those streams. Speaking of which, natural gas in manufacturing is rarely used as a flare. You rarely use natural gas just because you want to burn it and you want to have a flame. There is a reason why you use natural gas. It's usually tied to heating something. Product directly. So if you have an oven and you put a product through the oven and you heat it with natural gas convection, that's one way. The other way is for air. How many people have makeup air, or they have to heat air for the ventilation or for the paint lines or whatever the reason might be. Thirdly, for water. You can either heat the water, have hot water, or you can generate the steam through natural gas. So every time you work on a project that saves natural gas, you're inducing savings of electricity and water usually, not just natural gas. So therefore, if you, for example, if you're doing product directly, heating of the product in the oven, better heat utilization could lead to the less operating hours that you actually have to run. If you run less hours, you're going to save energy. Not only natural gas, but also electricity, also potentially water. Air. Air is moved with fans. What are fans powered by? Electricity. So every time we save makeup air, we actually save electricity and natural gas. Same with water. If you have less water to move, if you have less water to heat, you will have to move less water, your pumps will work less, and that will lead to electricity consumption reduction and water reduction. I have worked on the projects where we replaced older boilers with a newer boiler, and significant portion of the savings didn't come from natural gas. It actually came from the fact that they had old feed water pumps that were cooled by the circulating water that was just dumped into the drain. And they used 5 GPM in those pumps of water. 5 gallons per minute went down the drain every minute of their operation. One of the benefits working with our team that no other team provides in the conservation area is that we will actually work on your savings before you start the project. As a matter of fact, we prefer working with you before you put a business case together, because we will find all those savings. Our program, unlike electricity programs where you actually have to measure before and after, our program does not rely on that. Our program relies purely on estimated savings based on calculations. Natural gas is very easy to estimate savings for, and it can be done through the calculations. So when we do calculations, we will also do calculations on savings of electricity and water. And because they're calculations, we don't have to wait for you to implement it. So we will tell you before you go to your management, ask for $1 million investment, how much payback you will see. And there is no risk to you. Once we tell you that you will get some amount of money, you will get that money. Even if our savings are wrong, we will provide you with the money. So that was of the last 5 years. So what about the next 5 years? What will happen in the next 5 years? What will happen in the future? Can we make this better? Can we make this more successful of a program? You know, I put this slide together way before I knew that the guys down the aisle will have a conference called the Design to Disrupt. Disrupt is a very specific word these days. Everybody's disrupting something. My experience tells me that there is no such thing as disruption, especially in our field. We're bound by the laws of physics, and those can be not disrupted very easily. So to me, we will be forced to live with some sort of energy conservation one way or the other. Whether we do it for the cost reasons, whether we do it because it's the right thing to do, whether we do it because organization requires. We will have to do that. So how do we improve the results? How do we improve on 25 million cubic meters saved a year? I spoke about this before, and today we'll touch on this topic again. Cultural barriers. This is the only thing that's preventing us from saving more. It's preventing us, and it's preventing you. Okay? Sorry. So to talk about cultural barriers, first we have to understand how the project is usually done. In any project that I have ever worked, and I worked in a number of different industries, project flow is like this. You identify the need for something, you engineer the solution, you prioritize your options, and then you present your action plan. It's pretty much how it always works. Energy efficiency is no different. So we said, OK, if that logic works, following that logic will increase our results. So we specifically designed an air balance audit for the facilities. We said industrial heating and ventilation is one of the underdeveloped areas of energy savings in the province of Ontario. Almost everybody in this room, their facility can be improved in heating and ventilation costs. All of you overventilate by large amounts of CFM, of air. And all of you stand to gain a great savings if you actually go ahead and change that. The problem was, of course, that nobody knew how much that is. Nobody knew how many CFMs their facilities are using to intake through the makeup air or exhaust. And they had no idea how much their balance was negative or positive. So they wouldn't do anything. So we said, OK, to overcome those concerns, we will cover 100% of your air balance study, up to $7,500 at the time it was. And we will increase our financial incentives that for any opportunity that we find where you overventilate and you can save, we will cover, our incentive will be so high that your payback will be a year or less. So that was our offer that we started something around 2013, 2014. So why is air balance important? Informs decisions on makeup air requirements. Usually when you go and you talk to people about their heating and ventilation, they say, oh, I need this makeup air because it's smoky here, or people are going to die, or something like that, very dramatic. Well, OK, let's see how much you actually need. Air balance also helps with design and implementation of effective heating. Usually you have places in your facility that are really cold and really warm, and they never mix. They can lead to properly executed air balance actually can lead to improved shop floor conditions. We had a customer that had walkout in their facility. The facility was so cold in the wintertime, they actually walked out of the facility. So they wanted to put a whole bunch of makeup air. They wanted to increase their heating. We went there. We talked to them. After a number of meetings, we actually managed to talk them into turning off the exhaust they didn't need. They had, if I remember correctly, Slobodanka, you can correct me, but I believe 400,000 CFM of negative air balance in the facility. So, which means that 400,000 cubic feet per minute of cold air was infiltrating facility every minute. Of course, you're cold. So, usually these processes can lead to improved shop floor conditions. So this is what happened. Out of 41 sites that took advantage of the offer, 55% chose not to implement recommendations. Half of them, just over half of them. And recommendations were not very light or very fluffy. Recommendations like, you have 103,000 CFM of makeup air. You're exhausting 482,000 CFM of makeup air. If you just tied your process to your exhaust and your exhaust to makeup air, you could save $60,000 a year, and we will give you 50% of the project cost for simple payback less than a year. Another example was 172,000 CFM of makeup air for 410,000 CFM of exhaust. Again, $80,000 savings. They chose not to implement it. And we were surprised at that. We were like, why wouldn't you implement? Because this is the cost. Every 1,000 CFM costs you $1,680 annually. And that doesn't sound like much. $1,680 is probably something you can hide. The problem is, 200,000 CFM of unnecessary makeup air costs you $336,000 a year. Now, $336,000 every year in bills that you don't have to pay is a significant amount of money. Very significant. So we were, why is that happening? But it gets better. Those same people will then have something like this. Process require makeup air. They put the exhaust. They exhaust the process that requires that. Then they put the same amount of makeup air. Originally, when the building was designed, somebody designed it in this way, that whatever you exhaust through the equipment, you make up through the makeup air. That's where the name makeup air comes from. And those are balanced. Engineers who design this, who will sign off on TSSA and who will sign off on the building requirements, will actually have to design this. And they will design it that there's a balance between the two. But then comes the summer. And of course, in the summertime, this process that requires makeup air emits and radiates heat. So you have people saying, oh my God, it's so cold, it's so warm in here, I can't work here. So for plant management who has to deal with the complaints, the easiest thing to do is put up some more exhaust. You exhaust the air, you resolve the problem, everybody's happy, nobody's complaining, you're good to go. Perfect. The problem is, of course, winter comes. Now this air that you pulled up through the exhaust to get rid of radiation, now that air is not as warm anymore. So now you're pulling the cold air right through the building. And that cold air pretty much at the same temperature leaves the building because it doesn't have time to heat up at those air changes. It just goes right, cold air from right throughout. So what do? They say, I know what I'm going to do. The guy at the shipping area is complaining. I'm going to put infrared tube right above it. Good. True, radiant heat usually does not heat the air, but if you stand right underneath it, you will get the effect of warmth. So you have solved the problem of that one person at the shipping area. The rest of the facility is still cold. You have done absolutely nothing to help the rest of the facility. But it costs you natural gas and electricity to run this. So not only you're not saving on makeup air, you're actually paying more for electricity and natural gas. Air curtains, very similar situation. Air curtains work really well. The problem is if you have so much negative balance, you're pulling so much air that effectiveness of air curtains drops off to next to nothing. And if you put air curtain on one door, the air that has no choice but infiltrate because you're pulling it with your exhaust will come from somewhere else. So shipping door A will be happy. Shipping doors B, C, D, and E will be freezing as ever. And the rest of the facility. So you haven't solved anything. Yet we have people who wouldn't invest money into $80,000 fix, but would invest. Air curtain these days costs what, $15,000 to install? So you spend $15,000 instead of $80,000, but you solved nothing. And you added bills to your bill receipt. And my favorite result is they're saying, okay, we have to balance our building, so we'll balance it. Right now, we're paying $168,000 for the makeup air, for example. We want to balance it because we have 3 times as much exhaust as we have the makeup air. So we'll add more makeup air. Congratulations. Now you're going to spend $672,000 on your makeup air. So this was a big problem for us. We were like, okay, so you're willing to go to $672,000 instead of $168,000. What drives this decision? Because we work in these organizations that always we're being told, I was being told, I hope that hasn't changed since I left the industry, that to be competitive, we have to control our costs. Cost control is everything. We can't just randomly lose money. Yet you signed off on $672,000 for the bill versus $168,000 bill. So what gives? What's the difference? So when we actually looked at it, we said, okay, so projects maybe work this way. When you identify the need, you have a lot of external factors. Somebody's complaining, somebody's being the loudest. There's only limited resources. You don't have time to really look what the problem is. So if somebody's complaining, the easiest way to do is just to fix what's being complained about. Engineering the solution, well, if you already have predetermined idea what you want to do, engineering solutions will find the solution for that problem. And everything else after that just falls apart because wrong, garbage in, garbage out. Simple formula. So maybe instead of the project working in this way, maybe this is how the projects actually work in the facility. Has anybody seen this before? Because this has been floating in the industry for tens of years. So what actually happens in reality in executing this project is not that everything flows nice and everybody does their job. Everybody is usually worried about these two steps. Because if the facility is now paying the bills and nobody's asking you to fix the bills, you will not actually be, there will be nothing to your reputation if you keep paying the bills. It's easy way out. If you raise your hand and you say, I think we can reduce our bills, and you say, by how much? $100,000. And you actually reduce them by $90,000, panic ensues and search for the guilty because we didn't make $100,000 you promised us. We only made $90,000 out of zero. But you failed in your goals. So people usually don't want to do that. Because these guys here who did nothing get all the praise and honors. So that's what drives the projects, really. And what our workshops are designed to do, what our program is designed to do, let us help you not be the guy in number 4 step. Let us help you make sure that the project is success. And people from whom you will hear today have done that, have made that step. They actually took upon themselves to fix the problem, and they were very successful in doing so. So we obviously have barriers in our projects. And what are those barriers? Well, there are 3 categories of them. The first 2 are we just don't know enough. So they're knowledge barriers. We can't identify the need. We can't engineer the solution. We just don't know. So that's the knowledge barrier. The other barrier is resource barriers. Engineering the solution, prioritize the options. We just don't have it. We don't have budget. We don't have people. We don't have anything that's needed to actually fix the problem. So that's a resource barrier. And those are the easiest to fix. They're very transactional and simple to understand. Can you fix that? No, I don't have the money. OK. Can you fix that? No, I don't have anybody to work on it today. Perfect. So those are very fixable barriers, very, very easily overcome. All you have to do is you just throw enough money at it. I can give you money in incentives, you can fix it. I can give you money, you can hire people, you can fix it. That's easy fix. Speaking of our incentives, for those who don't know, they're designed to lower the financial costs of the implementations. So therefore, you will have, we contribute financial incentives towards the energy studies to find the project or to quantify the project in more detail than what our ESCs can if needed, or to decrease the project implementation costs. And those are usually based on annual volumetric savings and project costs, or combination of the 2. But there is money available, and you can actually overcome the resource barrier. But that's only part of the story. Even if I gave you all the money, and if you didn't know where your problem is, how would you spend the money? You wouldn't know where to look for it. You don't know what the opportunity exists. I can give you all the money you want. You will not do anything with it, or you will spend it very unwisely. So the other thing is implementation. You need to believe that what you're proposing will actually get you results you wanted. If you don't believe in that, you will not take the step of actually raising your hand inside your organization and say, I have a solution to this. You have to believe in it. And our job is to make sure that we give you enough information that you believe in it. So speaking of energy solution consultants, those are the people who will provide you that information. You know most of yours. For those who don't, feel free to get to know them in the breaks. But what we're trying to do, unlike any other energy conservation program in the province, or for that matter in Canada that I know of, is build long-term relationships with our customers. We want to know how you operate. We want to know what your pain points are. not on energy alone, what your pain points are in actual manufacturing. Because many times you have people who will not be able to speak in energy terms, but they will tell you what the problem is in production, and we can connect. Energy solution consultants can connect the dots and find energy savings in solving your problem. We want to understand your processes. Each one of your processes is slightly different. Even the differences between the places like GM and Chrysler, they do very similar things differently. We cannot just walk into one facility and say, this is how it's done. That is never going to get us anywhere. We need to understand how you solve your problems, and we will fit into that picture. And the third and most important part is we are providing unobstructed perspective. We are part of your facility, but we are not there every day. So we can provide that unbiased third-party view that you don't get if you're there every day and you're inundated with the same information. So we said three types of barriers. We only talked about two. So the third one is this, what I call a cultural barrier. And that's the barrier that I have a biggest problem with. Because if somebody is asking you, why would we change anything? I can't make any difference anyway. It's not on my scorecard. Those are cultural barriers. Those are not the barriers that you're going to resolve with money. Those are not the barriers that you're going to resolve providing people knowledge. Those are the barriers of people not wanting to do, not wanting to raise their hand. So how do we overcome them? Well, first of all, they're hard to identify. How do you know you're dealing with a cultural barrier? Because lots of people will say, we don't know enough, we don't have resources, or any of the other barriers, rather than saying, no, I'm not willing to step up and do it, be that in a management or in our own terms. So those excuses always hide the cultural barrier. And they're subjective. They're not something you're going to resolve with this spreadsheet. That's something that people either believe in or don't believe in, and spreadsheet will never fix that. So to us, this is how we found the cultural barriers. We give the money, we cover all the financial resources, we cover human resources, we give you the knowledge, we identify the project, we make a business case, and it still doesn't go. That's a cultural barrier. There's nothing else left. Everything else has been solved. So now that we know how to recognize them, how do we overcome them together? What's the best way of going forward with this? And we need your help with that. We need you to step up in your organizations as to say, this is how we're going to fix our organization. So to me, these are the keys. It takes an employee inside the organization willing to ask these tough questions. These are not easy questions. I'm not saying these are easy. I worked enough in the industry to know that raising your hand sometimes can be very difficult, and it can be not the best career choice, maybe. But people who ask why. Why do you need more makeup air? Why do you think that it's normal to have 500,000 CFM of air leaving the facility when only 20,000 CFM makeup air was provided? And all it takes is the question saying, why don't we think that 20,000 CFM of makeup air is not sufficient, rather than worrying about exhaust? And usually you will get, oh, air quality is so bad. Well, okay. It costs what? $500, $1,000 to actually check for air quality. Most of you will actually do air quality checks on an annual basis, one way or the other. So are you telling me that for 20 years you've been poisoning everybody, and now you're like, oh, I'm concerned now all of a sudden? I don't believe that. I don't believe that any one of us in this room has ever actually done something to hurt somebody. So I don't believe that that's how facilities are working. But even if somebody believes, I worked with a facility that was unionized, and we actually did the air quality study before and after together with the union present. We showed them that there is no difference. When we just shut down the exhaust. We didn't change anything. We didn't implement the project. We just shut down the exhaust. We tested the air quality a day or two after. There was no change. As a matter of fact, air quality improved in that particular case. But we worked with union, and they were like, yeah, okay, makes sense. It cost us extra $500 to do that. And it saved them thousands and thousands of dollars. People have to be willing to keep explaining to people both on the shop floor and in the C-suite. Why is it that this project is a good idea? But ultimately, it comes down to people who believe in an idea enough to make an impact, to make it reality. It's about people. It's not about technology. It's not about disruption. It's not about fancy Internet of Things. It is about us, people. We're the ones who can make a difference. So we have guest presenters today. We have two of them that I'm very proud to have here. So we'll start with Louise Bailey, who's going to present together with our friends from Chrysler. And I am very pleased to present Philip Messick, who is an environmental specialist. And they will present on some of the work that they have done over the last year or two. Philip, nice to have you here. Thank you.
All right, so I'm Louise, this is Phil. We're going to talk a bit about a project that we've been working on. Okay, so
this is the Brenda assembly plant over here. It's about a 3 million square foot facility with a stamping plant, body shop, paint shop, trim shop, and then all the things around it. The main gas users are heating, building ventilation, boilers, and then the paint shop ovens. There's some stuff going on the wastewater treatment plant, but those are the significant gas users at our facility.
So it's a really big facility with a lot going on. Sure.
Okay, so the plant was built in 1986. It's a good year. That's a 32-year-old plant. Our energy targets are gigajoule per car, and those targets are set according to the corporation, obviously, so we benchmark across all the automakers and our facilities. We're obviously a very old plant, so we are, from the beginning, we're set behind everybody when it comes to technology and improvements because we're working with an older infrastructure. So, as the last line says, it's difficult to make changes for energy consumption at times.
Okay, so they are quite an old plant, but as part of that, they've got a lot of experience. So we just wanted to do a quick mention of Bill Craig. He's one of the facilities people at Brampton Assembly, who we've been working with since the early 90s. So there's certainly a lot of experience, and there's some people at the plant who really care about, the success of the plant and keeping it running. Thank you. Okay, so over the years, myself and my predecessor have, at a very minimum, we've looked at pretty much all of the gas users in the plant. So we've looked at heating, ventilation, paint line, ovens, and also the ventilation for the ovens. We've also done quite a bit of work with boilers, which is what we're going to talk about today. Hot water boilers and steam boilers. Okay, so back 2015, end of 2015, we did a bit of a study with FCA. So we had found that as part of the analysis we were doing, that there was some condensate that was missing from the mass balance that I had done. So we went in, we looked at all of the end users, we looked at how much steam was being produced, and although the combustion efficiency of the boilers was actually great, we found that there was a lot of unaccounted for condensate in the system. So here's just a little diagram of the mass balance I did. We just got boilers, their phosphate area, and also the penthouse. The penthouse supplies a lot of the paint process.
Yeah. It's important. You gotta get going.
Sure. So as I said, the heat mass balance found that there was a significant amount of condensate missing. And even though the analysis was involved a lot of estimates and rules of thumb, the amount missing was large enough that we actually thought that there was something worth looking into here further. So the complexity of the system, you all saw the picture of the plant. It's huge. There's a lot of steam users in the plant. We felt like we should probably bring in a third party with a little bit more time and experience specifically to these systems. So when we were looking for some vendor to do a pretty in-depth study, we wanted somebody who could map out the steam system thoroughly, pressures, flows, for all of the end users. We wanted somebody who would then document and evaluate the condensate system based on what needed to be brought back to the boilers. Somebody who would also look at the flash steam recovery for opportunities there. And we wanted a clear list that identified potential savings, costs, and payback. So the plant went with Invino. So Invino is, I believe, owned by Swagelok now, so they have representation here, but they're well known for their expertise in steam systems around North America and I believe the world. So, yeah. So they brought 4 people on site, and they were there for most of a week. So that gives you an idea of the amount of time that was put into this study. So they did pretty much a full analysis of the entire plant. They were walking around, checking flows, making sure they knew every piece of equipment that was using steam. So at the end of the week, they did a preliminary findings presentation just so that the team at Brenda Assembly Plant knew what they were finding, and then 3 weeks later, we got a report. So we had a full steam system map, which was something, I don't know if you guys had that.
We have sort of different operational areas that had information. What they did was give us a full balance of where the steam goes, how the condensate comes back across the whole plant, which is what we really needed.
So they also identified the cost of steam. We can come up with some estimates for the cost of steam, but until you really look into the system, the cost of things like chemicals and condensate being returned, things like that, you don't really know the true cost of steam, and that helps then to come up with your payback for potential projects. Okay, so yes, so they started with they started into this list. This was quite a long list that ended up coming out.
So I think the biggest thing was to look at the payback on these projects and kind of start with the easy stuff, prove it out, and then we get momentum. Facility managers like Doug over here, they want to see quick payback. So the easy wins were things like steam traps, which should be checked annually. Ours had a failure rate of 36%, which is unacceptable given the volume of steam that we're pushing through. That's a huge loss for gas. So this is an example of our steam trap stations and the failed units. So the yearly cost is extremely high, obviously. You get a cost savings that you have the CO2 equivalent as well, which is going to become reported in 2019. So these guys not only identified these problems, they also did a root cause analysis, and they basically gave us immediate information on how to correct the problem. So for that, we had other issues, and they were able to identify suppliers and pay back on bigger problems as well. So we could present the business case to management and then implement the changes.
Just wanted to add something. On the steam traps, everybody who has a steam system has their steam traps, and you know that some fail. But what's really interesting here was that the failure rate was so high, pointing to some larger issue that needed to be addressed. Sure. So this is me. So basically, the issue that spurred the whole study in the first place was the fact that there was missing condensate. So that is also being addressed now. So basically what was going on was that so much had happened since the plant was originally built, and they weren't necessarily aware of where the condensate was being lost. So the study identified that. Yeah, so as it turned out, and I'll let you talk about it in a second, a lot of the condensate was actually going up, venting onto
The study not only helped identify issues that we didn't know about, but it highlighted persistent problems that weren't being addressed for whatever cultural reasons, we all know exist in our facility. So we can identify the problems as the managers in the facility, and at times you don't get the results you want for whatever reason. But if you bring in an external person to highlight the problem, you might get more traction because it gives you more people weighing in on the problem. And a lot of times your top-end management will listen to an external person because they can't beat down on them. So in this case, we knew that this problem was there. What Envino did with Enbridge's support was give us a true cost estimate on what we're losing and identified some safety issues associated with the problem. So it kind of gave it a bit more momentum. And as a result of the study and the work that we did, we were able to implement this project. And this one was expanded out. So I worked with Doug on it, who's the paint shop maintenance guy, and we basically did this one, and just to prove how quickly we could get the savings back. And I think that everyone likes that. That's pretty good. And the total cost savings, and as Damir was talking before, you bundle gas and or water with the gas savings. And again, in 2019, you add the cost of carbon, and you're looking at a really good savings. I mean, the cost increment was $16,000. And then we expanded that out to 3 more pumping stations for condensate, and we're implementing that one. So,
yeah, what Louise will build up these little spreadsheets that we show on. It's got to go in front of plant manager, has your money. Having this has been very useful for us. Showing them what the paybacks on you would be going forward a year. Showing them that they're going to give us 50%. Guys, how can we go wrong? That's been very helpful.
Thanks.
The CO2 so we are going to be part of that plan next year, and actually my metrics don't include natural gas. I have other ones, but what I do is I always speak to the CO2 equivalent, and I mean, to reduce that, you got to cut back on natural gas consumption. So it's easy. It's really easy. If you want to be part of it, you can do it. If not, you can lead, follow, get out of the way, right? So.
Okay. Well, yeah, you already sort of spoke about this. It's that if you don't know where to spend the money to fix the problem, then you can't spend the money to fix the problem. So removing the barrier of the knowledge gap is something that we did with this in terms of the study. Yeah. So no amount of incentive will help you if you don't know that the opportunity exists and know what the savings will and the results will be.
Oh, I should say this part. Without Louise, we want to trust it. As first time analysis, this opportunity to remain unimpressed and remain so for a long time. Thank you, Louise. Louise has been a great help. It was very good. So.
Okay, I just wanted to touch on this at the end of the presentation because this was something that was identified as part of the study. I don't necessarily think it's something the plant is interested in, but bringing a third party in sometimes gives you a perspective that you might not have considered. In this case, it was the potential of a steam turbine to get some electrical or some mechanical work out of the drop in steam pressure from their high pressure to their low pressure area, just as a neat example. Okay, so the study was a success. We got a lot of projects out of it. We only touched on a few of them here, but there's lots of things that will be done as a result. And in terms of natural gas, it really impacts the gigajoules per car metric, which is what you guys are concerned with. So it's all about those resource barriers in this case. And then, of course, removing the cultural barriers by the residents and the plants, people who cared. So Bill has put a lot of work into it, so has Doug and Kevin, who are here today, and then Bill Craig, who unfortunately couldn't make it. Does anybody have questions about this project?
How much was the study?
How much was the study?
Yeah.
It was about 45,000.
45,000.
Yep. Yep.
You're using steam for process load, or is it all just building heat?
Process. All process. Yeah. We use a little bit for a durator, and then there's a steam heating unit in the powerhouse, but it's all process.
And the building air supplies are all natural gas?
Yes.
Yep.
Just curious, how long did it take start to finish from when there was interest in the study to, I guess,
well, we had to hustle to make sure that we were incentivized for this. We also had, there were some production variables we were dealing with. So the study was a week, to get the guys in timing and to get funding in place was about 2 or 3 weeks. And then a week for the study.
Yeah.
And then a month for the final product, so about 2.5 months.
Yeah, they were restricted in terms of plant shutdown and things like that. But that initial mass balance that I did was end of 2015. So this work is still ongoing, so that gives you a bit of a timeline. Yeah. Anyone else? Cool.
All right. So.
We have an award to present to Chrysler for their exceptional work done over the last year or two especially. As I said, Chrysler has been more than a leader in this field, but in the last couple of years, this has really sped up. And working together with Luis, they have done some really great things. So I hope everybody got something out of this presentation. As I said, it's about people. It's about people who care. It's about people who are willing to push the needle forward a little bit. We have another presenter now shortly joining us. So we will take a 5-minute break. When we come back, we will start with the next presentation. Hope everybody enjoyed the first presentation. That I think was very useful, and again illustrated the point that you need to know where to spend money. The payback was so short, but only because opportunity was finally identified. And as Philip mentioned, third party came in and gave a little shove, a little push to actually get things done. So that's what our role is, to be that third party, to come in to say, hey, maybe you should be doing it this way. So we have another guest presenter here. We have Dominic from the Krupi, who is going to come in and talk with Chris Russell about some of the projects that they have done. He's a plant manager at the Krupi, and I am really pleased to welcome him as well.
All right. Good morning, everybody. My name is Chris Russell. This is my partner in crime at the asphalt plant, Krupi plant. This is Dominic. And today we're just going to go over some of the projects that they've implemented at some of their hot mix facilities in the Toronto area.
Okay, do you want me to say a couple words?
Sure, I don't know what. Fire away.
Okay, just for everybody in the room here, like going back to what Nazir said earlier in the presentation, Krupi has been around since 1951. We have a couple of asphalt plants in the Toronto market. And we are one of those older plants, older facilities that are having a rougher time competing in the industry. And I can tell you that we were probably one of those guys that Nazir mentioned that said that leave it the way it's running, we need proof, right? Like no disability from myself all the way up to management. So I can tell you that now that we've bought in and we're starting to make changes and you can see the changes, it's fascinating. One of the things that I can also add is the service that we've gotten from Chris to actually implement some of the projects that we have done. You'll see some magnificent savings. Also, I'm actually upset with Chris as well because when we're doing a modification to the plant and all of a sudden, you know, it's a great idea, we're doing it, then he comes up with another idea. You know, if you change this too, there'll be, like, you'll probably save some more money. And now that we've bought in, we actually have to redesign, panic mode, and then it actually helps us out there as well. It's actually a good thing. No, it's actually good. And then the other thing that I like to say is the tools that we don't have to check out some of our issues, like to make us believe that Enbridge does have the tools that they're able to come to the site to show us, hey look how much heat you're losing here. You're going to see some of the slides here that are pretty amazing that for me, I'm actually excited about it now with some of the things that we've done within our company to make us compete with an older plant that can probably be more efficient than some of the newer plants that are out there. And it also changed our philosophy of when we buy stuff now. We can buy some old technology or we can buy some new technology and then we look out for, you know what, instead of buying the old technology, we're going to go right for the newer technology equipment because we know there's a savings there. And that's what we've learned from this whole process. Okay?
All right. So here's just a This is one of their plants. This is a regular hot mix asphalt plant. The pictorial of what this actually looks like. This is my best diagram of how you can draw asphalt. So just as a high-level overview, a lot of people have some of the similar equipment to what you'll see in asphalt. This may not just be specific to this type of industry, but if you were to start from the back end of the process and work forward, we do have a bag house at the end that is effectively just a large vacuum. It's sucking through a gigantic fan, and it's pulling the heat and the dust from the drum dryer, which is heating aggregates to produce their asphalt product. So everything at the end is driving where the heat is being used through their process. So we have two main sources of heat in the plant. We have a thermal fluid heater that's circulating hot oil. In the case of the storage towers, you do not want any of your towers to solidify. So you have coils of hot oil that actually surround the outside of all the asphalt, waiting to be loaded out into trucks. And it also, you're sending hot oil to your drum dryer and up the loadout conveyor that sends it to the storage towers. Their largest consumer of natural gas is in their drum dryer. So that there consumes, I think that one's about a 135 to 150 million BTU an hour burner.
Yeah, just see it, and you can see that with our facilities, there's so many opportunities to actually save money, right from the exhaust system, from the dryer heating the aggregates. We actually heat up our aggregates. We have to remove all the moisture from the aggregates so that the oil can actually stick to the stone. And then you have the heater that's running 24 hours a day, every day it's running. So you can see where we have lots of opportunities all the way up to the storage silos and all the piping that we have.
So if we were to start with what the drum dryer actually looks like, here's a dryer. On average, it's about 8-9 feet in diameter, about 30 to 40 feet long, depending on which plant you're at. And this drum, in this case, this is one of Dominic's plants where during the production season, which is now usually May to the end of December, aggregate is inside there, you're heating it, you're producing asphalt. The radiated losses wasn't really a concern until we came and took a picture of what it's looking like. So this is from a few feet away, and the camera's picking up on the surface of the drum. We're still at about 523 plus degrees Fahrenheit on the outside. So one of the biggest quick opportunities you can do is insulate the shell of this drum.
And a lot of these plants are manufactured in the southern U.S. states, like in Florida, Tennessee, and they don't have the extreme weathers that we have up here, so they don't really consider insulation as a major item that they need. But once he brought the tools, Chris showed us, said, look at your drum, look how much heat you're losing. We were like, oh my God, right? And then you can tell the rest.
You try to quantify that picture, and you actually get somewhere around 85 to 90% of their annual consumption goes into that piece of equipment. So almost all of their plant, you should concern yourself with the operation of that burner on that drum. So there's radiation losses through our shell. The other issue with it is we've got losses through the inefficient material heating when we're wasting heat that's radiating out into the plant, so we want to fix that first. We have radiation losses, and we have exhaust losses because the bag house is vacuuming heat out of that drum. So all the heat that's being pulled out has to be made up by that burner going into a high fire mode. So here's just some more pictures of what the actual drum looked like. You can actually see the flame inside. It kind of looks like a rocket engine. So you're dumping you're dumping rock that's wet into one end, and you're tumbling it through a drum, and at the other end you've got a huge flame that's trying to evaporate all the moisture off of the rock, and then heat all those tons of rock up.
And the flame never touches the aggregates, so you're actually depending on the hot gases around and the radiation from all the steel to heat up all the aggregates. So you can see the burner is actually 15-20 feet inside the drum, and this is actually where the burner is. So that's where we focused a lot of our installation. We insulated the whole drum after the project. I don't want to talk about what we did, but after that, the savings were tremendous.
So here's another part that, outside of insulation, if you're looking at the inside of the drum, from my point of view, you've got a rotating drum that you're putting material in. What you want to do, how do you tumble that more effectively inside the drum? You'll add flighting. You see concrete trucks driving down the street, they have flighting inside that's actually mixing their material. Asphalt does the same thing. They veil their material inside, so the more rock and sand and aggregate that you can get through the flame more evenly, the faster you can heat, which is actually less time that material needs to be in the drum. So it's less energy that's spent to heat that volume of stone. So
remember, we were in disbelief at this time. So first thing is the insulation, okay, you can see it, there's hot gases on the outside, you can see it's the image shows you it's red, you put insulation on, you save on heat, okay, there's a savings. So how do you quantify like veiling the material inside? Who are you to tell me that, hey, it could be better? So he gives me the analysis, says, look, if you lift up the material and you drop and all that gas that's going through and you heat up more of your material, instead of sending the heat out through the back into the ducting all the way to the exhaust fan, you trap that heat into material, you become more efficient. So remember, like through the whole process, we're still in disbelief mode now. Okay, we can see that one. Now you're really telling us we can do this, and that's how the next step came about.
Their plant, being forward thinking, they bought a really aggressive type of flighting, which is amazing for their process. So in this case, they installed flighting. So just picture in an original drum would have like little pieces of angle iron inside, and now you've got aggressive looking buckets with teeth that are lifting and throwing the material as fast as possible inside this drum. So in this case, the drum modifications, increasing the size of the shell and doing a whole pile of things to it, about a $400,000 investment. But they were able to avoid almost just over 290,000 cubic meters a year from putting these more aggressive shovels and flighting inside. There's a cost of carbon that we reduced, and we were able to give them I think $22,000, so 4-year payback just on adding flighting. And we save 546 tons of emissions that do not go into Scarborough's atmosphere. Material drying, so this is the next part. Under exhaust losses, this is a baghouse in Scarborough. So what we did was actually if we back up here, maybe it's a little hard to see, I was just going to show you. Here's the fan that is doing all of the sucking through the baghouse and back to their drum on the other side of the baghouse. All of that induction that's coming from that fan that causes that draft is what's causing the flame on the drum to run at its highest setting. You kind of can't see it in the clouds, but trust me, there is one of these little puffs coming out of the top, and that is a source of energy loss.
So when we did the dryer, if you can imagine this plant, you can see a lot of asphalt plants, you see that big white plume of steam coming out. In the summertime at this particular plant, you'll just see vapors right now. And one of the other projects that we've done here, which is talking about with the fan, is this plant had 250 horsepower motors driving a radial blade fan. So because of talking with Chris and efficiencies on hydro and gas, and we mentioned that earlier, like working together, on this particular project, what we did is we changed the fan to a backward curve. It's supposed to be more efficient. So because it's more efficient, I could utilize one 200 horsepower motor, which actually turns a lot slower and it's a lot more efficient, so I don't need the horsepower to actually turn my motors. On top of that, because of the fan, we got rid of our damper and we put a variable frequency drive on the fan. So now, instead of sucking full, let's say a full 1800 RPM with the fan at 76,000 CFM all day long, we now vary it down to whatever we need. So if we don't need all that suction, instead of doing it with the damper, we're doing it with the variable frequency drive. This particular plant here, the efficiency on this was tremendous as well, won't you show you? But this is the problem where Chris kind of gives me a hard time. See the red duct right there? So I'm doing this project. So you can imagine this duct. If you look on Google Earth, you see the duct was a lot taller, sloped down, it was a lot further. He said, if you get rid of 10 feet here, you get rid of 10 feet here, we can actually, I've already got my plant designed. I got to move my footing over now, I got to move my plant over. But you know what? At this point, I'm starting to believe, and there's actual savings. And this particular plant here, there's another part of the project, I don't know if it's on the presentation, but this last month was extremely wet weather, and we've actually had a savings of cubic meters of gas per ton of asphalt compared to last year with a lot more rain this year. So not only are we efficient, even when it's raining, we're still more efficient than last year. So that's the other project that we did. And Chris told me, well, if you do this, you could probably save a little bit more energy. We said, okay, we did it, because it's actually true, it does work.
Proactive. We should have got to him a few months earlier, but we'll see this December.
And you can see, like the baghouse, we're insulating everything now. Not only the piping, you can see the baghouse, usually they're just open pieces of steel. We insulate everything at the plant now. Whatever we can insulate, we insulate it.
This was one of the first VFD projects. It's the first asphalt VFD project that I had, but the logic that Dominic was using, if you think of how a plant used to run, when you start in the morning, you come in 6 a.m. or what have you, you want to get the bag house up to temperature. So you've got the drum already starting, the bag house is starting, you're getting your process running. You come in, you turn the fan on, and it just runs until you turn off at the end of the day. So you could be running, Dominic says you could be running 76,000 CFM for 10 hours without stopping. But when you have a slowdown in material production throughout the day, or say you don't have a few trucks for a couple hours or what have you, you can now actually vary the speed of this fan, which in turn, because you're not pulling as hard through the bag house, through the dryer, the drum itself will actually turn down. So yes, you're saving the electricity by not having to run the motor on the bag house for 10 hours straight, but you've got the burner on the other end and the fan for the blower on the other end. Everything in the plant can actually turn itself down. And fun fact, when I used to drive to the plant, you could hear them out in the neighborhood that surrounds them, and it would sound like a jet engine running all the time. Everybody wants to be a good corporate citizen. You now pull up and you actually think the plant isn't running. The VFD has turned down and the backward curve fan has actually cut enough noise that I'm actually worried when I call them saying I'm here to see the plant running, and I believe that it's not running because you can't hear it.
You can't actually, before, just around the whole perimeter on the roads around the whole property, you can actually, if the plant turns on, it's like a big jet engine. The burner, like now we have a quiet burner, we have the exhaust fan, the backward curve, the VFD, you can't even hear the plant right now. You can actually go right up to the plant. Is it running? The only way you can tell is if something's turning, or you hear some of the squeaking noises now because there's so many moving parts. But before, it was drowned out by the jet engine, you know, like the exhaust fan going full out. Now, that's a benefit that just came, not only on the efficiency side, but now it's on the noise side. It actually worked out great for us.
Less neighbors complaining is always a good thing. So here's, this is the project actually at that bag house from a few years ago. So Dominic and I, when we were working on the savings for the VFD, cost them about $260,000 to modify, pulling out the fans, putting in the VFD, doing the ducting. Their benefit was just over 717,000 cubic meters. So that gave them an incentive from us of about $43,000. And without the carbon costs, they're saving just under $200,000 a year in savings from their drive. 1.1 year payback, and they save 1,345 tons of not emitting into those neighborhoods. Another VFD project at another plant, which was the first picture you saw in the slideshow on the other side of the city. This one costs only about $48,000 to install the equipment. Again, removing the damper and putting in a VFD and modifying the electrics on the motor, saving them about 366,000 cubes a year. And that's, we're going to give them $24,000 for that. I haven't given you that yet. Again, 0.4 year payback.
And this project here was done because, see, the other plant that you saw was 1974, so it's older technology. So to justify to do it, it's like, come on, is that true? So that's where we got into that, let's do this, let's try that. This plant is a newer plant. And because it didn't have that technology, we decided, let's do it. And this is what we did last year.
There we go, saving another 687 tons of emissions and 0.4 year payback on this project. Now we'll get into the fun one of, this is a side of their process that other people in other industries, you might have this. You might be storing product outside. You might have material that comes in from rail cars or what have you at a colder temperature, and now you need to either heat it or you need to dry it or you need to do something with it. We can all see the benefits of insulation and VFDs and modifying equipment. This part solely talks about the fact that they keep rock and stone and sand outside. It gets rained on, it's covered in snow. They have to turn that into a usable dry, hot product. So there's a few ways that we can do that here. So this is the plant that you saw at the very beginning. This was just from their front gate.
So this is the actual property. If you look at all the stockpiles that are along the big giant black pile here, those piles right there were all along the whole side of the property. we've actually expanded how we store our materials. So actually, you're going to be talking about that next. Okay, all the stockpiles were on a flat surface, and all the water was sitting in front of all the piles. And we also took into account the sun, which way it's turning. So we moved all the stockpiles. So imagine trying to convince an owner it's worthwhile to move your stockpiles. It's virtually impossible. You're in the paving business. Let's slope our stockpiles. Let's move them, build new bins. You're just wasting money, right? Or let's pave them. We got paving equipment. You know how much it costs to pave, right? But then all of a sudden, you start showing the math. But now, because you believe in it, right? We do it. This is probably one of the simplest things to do that saves the most amount of money in our industry. I don't know if there's comparable industries. But to remove the moisture, the more I can remove before I put it into my facility, the more money I save, because now I don't have to dry it. So specifically, sloping the stockpiles, there's a huge savings. I think it's about on 2% moisture, I'm just doing it by the top of my head, it's about, let's say, 2-point-something cubic meters per ton, I'll say just on moisture reduction, okay?
So you're just kind of, like just for the scale of it, at the top, even way up in the corner is a transport truck with a full trailer, you've got a couple vehicles parked up there. So the pile, like these piles are in the hundreds and hundreds of thousands of tons of material. And if you think on average that sitting outside in our environment, it'll collect just by nature of sitting outside, about 5 to 6% of that pile will be water. So if that was a 500,000 ton pile of asphalt that's getting ready to be reprocessed, 5% of that will need to be evaporated. So those tons of water that you don't need to put into the process, if there's a way of removing it beforehand, we did it by sloping. If not, you've got to put it into that drum burner and evaporate it by using more natural gas. So this is kind of, there was a paper that was done for the asphalt industry, and it kind of says that for every 1% increase in those piles of RAP, which is your reclaimed asphalt product, I seem to get that wrong, which is just regrinding parking lots and different sorts of, wherever you see like a resurfacing project going on, that is the reclaim. They don't throw it out, they'll actually grind it down and reuse it. It's great, it's environmentally friendly. But for every 1% of extra moisture that you can get in that pile, it adds about 10% energy usage on that drum. So we really want to control the amount of moisture right at the beginning of, if you can get rid of it or cover your material and not let it get wet in the first place. So the one we want to talk about just really quickly is stockpile sloping. If you can imagine those piles and how much they would weigh if they're 500,000 or 1 million tons of rock and sand sitting on the ground, eventually you will dish the ground. You'll compress it and you'll make a bowl. As everything rains and snows, you're now keeping everything in almost like a bathtub. So what we've done, or what Krupi has done, is they've taken their piles and underneath, to Dominic's point, they've actually removed all of those piles of material, graded at about 2-3% of sloping their ground, and then paved their entire portion underneath these piles to allow moisture to drain away just by using gravity. Conversely, you can cover it and try and prevent moisture from getting into your material in the first place. So this is actually the project that you were talking about. We regraded their yard. They regraded their yard. I wrote the application. So they spent about $49,000 in moving the material, grading, paving, and it saved them 130,000 cubes in natural gas. We gave them just over $19,500. It was a 1-year payback. It's a great project. Just by letting gravity remove that water, you save 243 tons of emissions. Maybe I'd like to say that too, just for the asphalt side of this. The 5% moisture, so if we were to have 5% moisture in our rock as we're putting it in, that can actually hinder their production up to 36% per hour of their throughput.
So yeah, as slow as, let's say, if a plant could do 400 tons an hour, all of a sudden, it depends on how much rain, you can drop down 300, 200, sometimes you might have to shut down because there's too much, because your exhaust fans can only get rid of so much moisture. So the lower amount of water you put into your system, the less moisture you have to get rid of, the faster you can operate, the more you can dry.
One that affects quite a lot of us is our distribution system. In this case, for your own industries, if you have steam pipes, in this case, asphalt has a lot of thermal oil pipes. very hot oil, and to Dominic's point earlier, plants that are built in the lower states, they don't really concern themselves with our atmosphere. A lot of piping comes uninsulated just by virtue of that's how the plant is made. Dominic's taken it upon himself to insulate every square inch of his plants, because right now we're radiating out into the atmosphere, so how do we control that? When you've got silos that are holding thousands of tons of asphalt, and that's where you want to be ensuring that your product doesn't solidify in those towers, because I'm assuming that's a nightmare if you have storage towers that are solidified asphalt that you can't get out. So all of your heat, you're trying to transfer to those towers. Any heat that's being lost and wasted to the atmosphere, we could have been putting in there and turning down the thermal heater. Our towers are also heavily insulated, and yet they also still radiate. So unfortunately, to Damir's point, you can't escape physics. So we have insulated these towers. This is that plant that had the aerial view of all the asphalt sitting outside. But when you stand back at this distance and take a picture of it, you're still radiating no matter how much. But imagine that this plant was purchased with towers that were uninsulated in the beginning. These are heavily insulated now, and you can see that we're still radiating. So for a storage tank that we want to insulate, it's going to cost around $30,000 to insulate this, but we're going to save $55,000. So for a 0.4-year payback, and I'll give you 15 of that $30,000. I'm pretty sure Dominic's going to go ahead with it.
And then one of the things here, all these savings that we're getting for all the projects that we've done, it's continuous. Those savings are coming in year after year now, because we've noticed that our gas costs, even though if the gas costs go up, we're still going down in consumption. So our total cost to produce, we're now, I would say, more competitive with any new production facility that's in the market right now. So we have an old plant that could probably be just as efficient or better than some of the newer plants that are out there right now.
Saving, just insulating a tank. So for every hour that this thing is insulating, they save 414 tons annually of CO2. So just as a kind of an overview, there's like the pictorial of how it works, but it's not just specific to asphalt. Like they do have rotating equipment, they do have piping that they needed to insulate, they do have, in our case, where we were talking about building exhaust and CFM imbalances, the baghouse and asphalt, that's where that part comes from. So I mean, if you can kind of take these back to your specific industries, everybody has something of this form of equipment or this kind of a layout that there might be some sort of an opportunity if we were to look at it the same way that the asphalt industry does.
If you looked at the two plants, the one that had the red duct on it, if you looked at the second plant, it had this big structure over top of the round drum. Well, that structure is not on the old plant. We removed it. It used to have it. We just go right into the old drum. Now we have a little separator inside to do. That's how we reduce the size of the ducting, and we put a separator instead of having that. That actually separates coarse dust from fine dust. And that other plant still has it on top of the tower, and that's going to probably be a future project that we're going to be doing.
I'll take you up on that.
All right.
Does anybody have any questions about it? Yes.
Dominic, I admire your passion and enthusiasm.
Dominic, excellent project. Christian has done well. Remember, obviously, we're in the same situation. We got a very good plan. How the hell did you sell the 4.4-year payback over the very original slide from the drill machine? That's a very good job on that one, because if I go to my boss on that one, I would love to.
I think he's got a very good. I think he's got a very good, close working relationship with the owner.
But I can tell you, the slides, well, this is Chris's fault. He should put the slides in order. The way it started, our first one was the sloping the stock wall. That was the easiest one to do, right? So that was you got to buy in first, because I'm not gonna lie, I'm negative. I was negative. I didn't want to do it, right? I said, come on. Right, yeah, really, they show me these charts, everyone shows you these numbers, there's from the internet everywhere, right? Yeah, come on, right? Until you buy in the first time, I can tell you now, I'm bought in. I believe in it because it's dollars and cents. You can actually see the savings. So when you do this type of stuff, it works. Like, you just have to believe in it, look at the numbers, and then you know that little slide that Nazir had with the little panic? I'm always in that panic mode every year. You know why? Okay, did it work? So I look at my numbers every month saying, okay, yeah, we're going. Yeah, we're less than last year, we're better, okay? And that's the thing that we do.
And that's one of the most valuable things, having those incentives and having that payback. For when I go present that to the board, this is their payback, this is what it's going to cost, and yeah, it's going to be 0.4 a year payback, or too. I love your cell 4x4, good job on that one. But that's the exact information that I need.
It's tangible, right? Like Damir said, we've never had that before. We didn't invent these formulas. Like we do it. It's mathematical. That's real.
There's only CDs, and that's what they want to see.
Right.
Your drum processor, Dominic, is that the batch processor or is it like a flow?
The first plant that you saw was a drum plant, a complete drum plant. The second plant with the red ducting, that's a combination plant. It could do drum mode or it could do batch mode. And some of the things we've done on the second plant, we actually had 2 drums, an elevator, right? And that's where we did, okay, we're gonna do all this. My God, I spent all this money, but I moved it closer to the bag house. The ducting we reduced, I got rid of a whole drum and a whole elevator. So now when I do batch mode, I don't go up, I still have to go up the elevator, but the batch mode, I probably operate it now 5–10% of the time of the year. It's all drum mode because it's one drum. It's easier, it made it easy for the employees to operate as well. So there's other benefits on top of the one that we talked about is the noise.
Yeah, what I was wondering is with the VFDs that you have there now, maybe it's not an option for you guys to slow down the process, if that makes sense. Or you guys just pretty much balls to the wall when you're running and December's coming.
Yeah, right now, our busy season is mid-August to probably mid-November, but this year, because everything started late at the beginning of the year, I don't know if everyone remembers, it was cold and snowy. We're actually going right into, probably go right into December.
Yeah. I know not asphalt, but cement plants, they end up with problems with their aggregate too, when they actually heat it. So have you looked at maybe using your waste heat to preheat it? Was that a possibility?
You know what? It's his fault again, right? That exhaust stack, he just went to me now. So we got this new technology bag house. So that bag house that you saw with insulation on it, we used to have a whole bunch of pipes that a compressed air blows through these pipes to clean our bags. Now we have this bag house called the reverse air. So what it does, it sucks air from the atmosphere and blows my bags. But if he really did a good job, he would have told me before I did it, so this way I could fix it. All I have to do now, he goes, why don't you put a piece of duct from your exhaust stack, go right over top of all they're sucking air from ambient air, why don't you take the hot air and suck it back? It's clean air going on anyway. I said, why don't you tell me that before we did all this?
Job security.
Right? That's actually a good point that he said. That's part of one of our next projects. We have to put like a duct from the exhaust stack over top of, there's these 4 ports that suck air from the atmosphere to lower back. So we use no more compressed air on our bag houses. So we got rid of a compressor and all the air. We're introducing air that we had to get rid of with our exhaust fan. Now we don't do that anymore. That's a great question. Yes?
I have a question about your VFDs. When you operate your VFDs, do you run it on automatic mode or does the operator still do it manually?
We automatic and manual, but I prefer automatic all the time. Because what happens is, see, it's always human error. So if the VFD works automatically, if the burner is turning up because there's more moisture coming in one end, the exhaust fan doesn't know until later, right? So if you're an operator, you leave it open. But in automatic, if the burner turns up, I gotta get rid of some air. But if the burner starts to turn down, in our process, it takes like 5 to 7 minutes before the exhaust fan knows what it has to do. So with the automatic, if it starts to turn down, it knows, it keeps everything in balance also. There's other benefits that have been happening on top of just energy efficiency. We noticed that our dust flows are better, everything's more consistent, our mix designs are more consistent, we're controlling everything right now. So there's other benefits that happen that we didn't expect. And that's probably why I'm so excited about it.
So when you do automatic, when you run it automatically, that's when you have its benefits?
Yes, yeah. It is, it's excellent. Yes, sir.
Would you have to bring in a specialist to help you figure out VFDs, or are there specialists in the asphalt business?
Well, Chris helped me with a lot of it. And just looking on the internet, talking to manufacturers, saying, what kind of fan would you suggest, you know, and then Chris saying, hey look, there's this in the market, so he's been an encyclopedia for me, I have to say that. Thank you very much.
It's his fault.
Yeah. It is. He tells me things late, like they gotta tell me ahead of time.
I want to make you look good next year.
Okay.
What kind of controls do you use, Chris?
For
VFDs.
So they've got a full DCS, which is actually, they have a vendor that's actually specific to the asphalt industry, aggressor automation. Yeah. Their whole bread and butter, their niche is just setting up and controlling asphalt. I don't know, I think they might use Honeywell, but they've got their own kind of proprietary system.
The guy's amazing. Remember, we have an old plant, so this is old technology. You can go to my plant right now. My plant. It's the ownership's plant. I work there. But you can actually push on the computer control, start, plug in the mix, and as long as you control the burner, you can run this plant right now. Because of the automation, it says turn on the cleaning, turn off the cleaning. That means the dust in order to clean the bags. And it produces all the mix up to put in the select which solid he wants it in. So we've actually automated the plant because of all this as well.
Any other questions?
Yes, sir.
I didn't see anything there where you're storing the liquid products. Is that what the silos for? Is that all finished?
On the opposite side of the silos, let's go to the first picture. Go right to the first picture. We got horizontal and vertical going back.
Keep going.
Yeah, right next to the first picture.
One more, two, three, two,
one more.
One. Nope.
Almost there. Okay.
Oh, sorry.
See, this is a vertical tank, and these are horizontal. Inside those tanks, if you look at the bottom of a barrel of crude oil, that's what's inside these tanks. It's called asphalt cement. That asphalt cement, it can be hard as a rock in the wintertime. I can break it with a hammer, it'll shatter like glass, but we have to keep it in liquid form.
So you didn't have that in your schematic, though.
No,
if we go back through where insulation is, insulation wraps around their silo towers. It does actually, they have thermal coil around the tanks.
And you're running the heating oil through there as well?
Yeah. Yes.
Okay.
Another project we're looking at right now, probably for next year. You notice, if you go back to the first picture, see these two tanks here? I might get 4 vertical tanks and get rid of those, get rid of the horizontals. Because if you look at the horizontal tank, you got all the heat loss along the whole horizontal instead of a vertical tank. So like, if you look on the internet, it tells you there's a huge savings here, right? This is what it is. And so that's what we're looking at right now, see what the payback is. And that's another project that we're going to be looking at.
What's the story about that red duct? How is it saving you more?
Oh, not that red duct. Okay, go back to it.
Why don't we look at it?
Okay, oh, wait, this is good. Remember the red duct? Yeah. See this item right here? This is called a knockout box. So this is the back of the drum is behind this picture right here. So all the vapor and the dust go into this box here. This gets rid of all the heavy dust, around 600, maybe less than 600, like 600 minus. It drops in here. Then all the 75 micron dust goes to the bag house, all the vapor, and then all the steam, all the vapor goes out, turns back into steam, and that's what goes out into the atmosphere, and all the dust goes back into the mix. But see, all this, and all this is all the heat loss. So we got rid of all this duct, right? So, but now we had ducting. So we had a ducting that just went like this right to the back of the drum, and this thing here now is right at the face of the bag house. All the dust gets separated just before it goes in. But all that ducting that's missing now, right at the end, he goes to me, why don't you just shrink it and move it closer as well, right? Because then any time you have X amount of pipe, right, that's not heated, something in the future, so inside this box right here, right beside the bag house, it's not in midair anymore, it's actually right here. And then this duct used to be, let's say, up to here, and this used to go probably out to here. And that's what we reduced.
So it's, you're bringing, the dust, the coarse dust back to your product.
Correct.
That's what the duct
Yeah, so all the coarse dust falls right here, and right below this item here, there's actually, in this particular appliance, it's actually a little bucket. It used to be augers. Now we use a little bucket elevator, which is also more efficient, because everything is now like really tight. So all that heat is all in one area right now. So this plant that was actually spread out is now we just brought it all together. So everything's nice and tight.
I guess just to give you like a crash course really quickly, you can correct me if I'm wrong. Bag house being a huge vacuum system, there are monstrous filters inside here. So this air comes in and goes up through the bags, and the dust gets stuck on the bags, and then the air gets pulled out and exhausted.
And the reverse air in this one here shakes the bags, and all the dust goes back into the mix.
If that bag house drops below the dew point, you'll start to condense all that hot air in there.
We have to stay above 225 degrees, let's say.
If those bags, and everybody in asphalt can contest to this, if that, because you are losing heat across that duct that's radiating out into the atmosphere, so the less ducting, knockout boxes, and everything we can have on a bag house, the hotter that air is, and we can keep going through the whole system. If that cools down on those filters will mud. All that dust just coats. Bag house no longer starts working. The fan starts to pull even harder. The burner turns up, and everything falls apart rapidly, and then you're shutting down to go and change filter bags because they're covered in wet mud instead of dry dust. So the hotter we can keep that air coming in at the beginning, we can alleviate shutdowns unnecessarily.
But you gotta do everything properly, because it's all about balance. Inside those drums, remember we talked about the flighting? If you go too efficient, you bring the temperature down too much, you actually create mud and water in your bag houses. So some people, instead of adjusting their flights back a little bit to maintain that temperature or insulate your ducting or doing something else, they actually add afterburners either at the stack or here just before it goes in. So waste more gas. They make it efficient, then they waste gas to make it efficient again, right, for their operation. So there's ways of working out. So it all has to be part of balance on the whole plant.
Science. All right. Any other questions?
What's the temperature of the exhaust gas going in at the time?
On this particular plant here, we try to maintain about 250 degrees Fahrenheit. In the summertime, it could drop a little bit, but that's why in the summertime, with the vapor going through, turning back into steam, you'll just see vapors coming out of our stack. You won't even see it. You won't see our plant right now, and you won't even hear our plant.
Right. Any other questions? No? All right. Thank you so much.
So again, thank you to Dominic. Thank you to Phil. Thank you for presenting today. I think that is always great to hear customers talk about the successes that they've done. For those of you who think, oh, this is an asphalt plant, has nothing to do with me, yes, it does, really. Technology is the same. The way to save energy is the same no matter what we do. You know, we talked about insulating the hot surfaces. So you don't maybe have a drum dryer. Maybe you don't have outdoor plant. How many of you have steam pipes, condensate pipes, all sorts of pipes that need insulation and would benefit from it? Storage tanks for the chemical storage. Maybe you don't have a dryer. Maybe you don't know what a drum dryer is. But maybe you run Class A oven, natural gas-fired convection oven. Same thing applies. When you really think about it, of all the energy that you put into that oven, 44% goes into the exhaust. And that's a well-run oven. Right? So you're losing almost half of your energy going up the stack for no particular reason. We can change that. All of you have ability to change that, because at the time when these ovens were built, VFDs were very expensive proposition. So nobody put them on. So you run your oven based on your purge time. Nobody wants to wait for oven to purge for hours and hours. So you want really a lot of air quickly. So you run the purge time. All your exhaust requirements are based on the purge requirement. And then what happens, you have to purge it 4 times the volume in very quick succession, so maybe 10, 15 minutes at the most. But then you run like that even when your operational requirements are much, much smaller. So if you put VFD on now, you retrofit your oven, you will be saving almost 20, 30% of your energy that you put into the oven. So VFDs on the bag houses, VFDs on the ovens. Same technology, same idea, very good savings for relatively small investment these days. VFD on 5 horsepower motor is very inexpensive these days. Is there any questions or comments on technology or savings? Yes?
So can you explain again the purge of 4 times on the volume column?
When you run your oven under the TSSA rules and under the American NFPA rules, what happens is every time you have natural gas-fired appliance, like an oven, before you can light the burner, you have to allow fan to exhaust 4 times the volume of that oven. And because that purge takes time, nobody wants to wait. You don't come in the morning and wait for 1.5 hours for your oven to be purged. You want it purged in 10 minutes. Now that volume stays because you don't have VFD. That volume stays even when you're operating your equipment. But operational requirements are nowhere near the purge requirements. So if you can slow down your fan, you can slow down the amount of air that comes out of the oven, you save energy. Better?
So we oversize the fan just to get the purge going faster.
You always have to get products of combustion out of the oven, if nothing else. Most of us, luckily, today don't have any more requirements for example, the solvents in the paint because most of us use powder paint, so there isn't really that much solvent in there. But even with that case, you can save energy. Yes?
So this is just for my clarity also. So the exhaust fans, they're designed for operations, but for purge, or for, let's say, for the purge cycle, you don't need the full operational exhaust for the purge cycle.
The other way around, yes.
Sorry, the opposite, yeah. So that's why you can use a VFD there.
Correct.
Awesome.
Correct.
And you will have, for example, these fans will be on a typical oven. Paul, where's Paul? Is what, about 5,000 CFM or so? 4,000 or 5,000 CFM is the fan, but we really need maybe 12 to 1,500 CFM in operations.
And my motors for most of mine are about 100 horse and up.
Yes, for your oven, completely different. You have slightly different things. But typical paint line in a regular manufacturing shop is much, much smaller than that. Even for your oven, I think it's smaller.
We look at this. We have some ideas for this.
Right. Because remember, we're not talking about the supplying of the air. It's just the oven exhaust. Any other questions or comments?
You know, I got a catchphrase for both of you guys is just for emissions reduction is help save the planet. It's the only one with paved roads. Think if we had to pave Mars.
All right, so we have one more presentation of the award. I'm hoping we're going to have just a brief overview of the savings, but I just wanted to bring this to almost close today, but we'll have a couple of words after this award. But I wanted to give a special thanks, special recognition to people at Brandfeld and Holger especially. We have a program that we call Comprehensive Energy Management now for 2 or 3 years running, and I can tell you that nobody has implemented it better than people at Brandfeld. And I felt that it's really important that we recognize them. Holger has done a presentation for us last time in the workshop. He has done presentation in other venues for us, but it's not the presentation that we're really worried. What I'm really grateful for is all his work that he's put into fixing the problems that they had with energy and how much energy he had saved. So I would really like him to come up, and I will present him an award. Good to have you.
Thank you.
Thank you.
Surprise. Thanks. Thank you.
Thank you.
Thank you.
Thank you very much. So you've seen some of the savings that Brandfeld has achieved in the video at the opening of our shop today. He has been continuously working on ever more improving, and I think they're now somewhere about 30–35% savings. That is amazing. 1/3 of the energy saved. And some of the things that Holger has done himself, we often have questions from people at the end of these workshops or to our ESCs, who can I get to do X for me? Well, I can honestly say that I've never seen anybody who does as much as Holger. He goes out there, he buys the meters, he installs them, he makes sure that PLC reads what he wants them to read. Nothing beats the people. It's not technology, it's the people. So back to that air balance campaign lessons that I was talking about at the very beginning, where some people decided not to implement and we figured out why is it that they don't do it. Well, 18 sites did implement the recommendations. And of those 18 sites that did implement them, these are the savings that they achieved. So 22 projects, combined savings of 3.8 million cubic meters and 2.4 megawatts. These are large numbers. And this is only from your heating and ventilation systems. It didn't touch any of your process. It didn't disturb anybody. In most cases, it actually improved shop floor quality, if not maintained the same. So there is something positive to take out of those. So for those 41 sites that didn't implement it, they should really learn from this. These guys saved $1.3 million. And you might want to wonder, well, what did I do? What did they do to save that much money? They turned off the makeup air. They turned off the exhaust. We talked about the baghouse and how it exhausts the air. You can take your dust collector. Now, the air on the other side of the dust collector is clean. Otherwise, you would not be able to emit it. You take the dust collector air on the outlet, and you put it back into the facility. Given that most dust collectors these days are 20,000 CFM or so, you don't have to make up 20,000 CFM of air. You just put it back into the facility. It's the projects like this that generated these savings. It was never the D-strut fans. It was never the air curtains. It was never all those technologies. It was just simple, use what you have efficiently. Air compressor heat recovery. How many of you have air compressors? There we go. Put a duct on it. Duct it back into the facility instead of exhausting it out and then putting the heat into the facility that you pay for. And you don't have to do it alone. We get it that this is difficult. As I said, it is difficult to raise your hand. It's difficult to be first to do something. But that's why we're here. We have resources available on our website. You can show it to your bosses. You can say, here, somebody else has done it. You can be guest presenter. We had 2 today. We had Holger before. If anybody has any project that they would like to talk about and share experiences, please let us know, and we'll put you on the next workshop. And one of the things that I wanted to put, we usually take great care in preparing these workshops. I do every slide myself. My team helps with all the case studies, with all the ideas, with all the experiences. So we don't take this lightly. Except this is a 5-year anniversary. And what I wanted to do is I took the slides that we've all seen before. Today's presentation was a mix of all the presentations we've done before. So you've seen all these slides. This is not the first time you've seen these savings. So now is the time to make the next step. Take the knowledge and apply it to actual project implementation. So we can provide you with the guidance, with the savings estimates before you ask for money. We can talk on your behalf. If you have problems with upper management not approving something, let us talk to them. Let us talk to your shop floor personnel if need be. We'll do presentation for shop floor personnel at your facility, and we work with you on what and how to present the message. So let us help you with this last cultural barrier, because that's really what's preventing us from further savings. That's all I had. There is one more thing that I would like to do before we all go away. There will be a special 5th anniversary cake coming up. So in the meantime, is there any questions or comments that I can help answer? Cake will now be served.